My goal for the next two segments is to show you that if we use a secure PRG, we get a secure stream cipher. The first thing we have to do is define what does it mean for a stream cipher to be secure. So whenever we define security, we always define it in terms of what can the attacker do and what is the attacker trying to do. In the context of stream ciphers, remember these are only used with a one-time key, and as a result, the most the attacker is ever going to see is just one ciphertext encrypted using the key that we're using. And so we're going to limit the attacker's abilities to basically obtain just one ciphertext. And in fact, later on, we're going to allow the attacker to do much, much, much more. But for now, we're just going to give him one ciphertext. And we want to define what does it mean for the cipher to be secure. So the first definition that comes to mind is basically to say, well, maybe we want to require that the attacker can't actually recover the secret key. Okay, so given the ciphertext, he shouldn't be able to recover the secret key. But that's a terrible definition, because think about the following brilliant cipher. So here, but the way we encrypt a message using a key K is basically we just output the message. Okay, this is a brilliant cipher. Yeah, of course, it doesn't do anything. Given a message, it just outputs the message as the ciphertext. So this is not a particularly good encryption scheme. However, given the ciphertext, namely the message, the poor attacker cannot recover the key because he doesn't know what the key is. And so as a result, this cipher, which clearly is insecure, would be considered secure under this requirement for security. So this definition will be no good. Okay, just recovering the secret key is the wrong way to define security. So the next thing we can try and attempt is basically to say, well, maybe the attacker doesn't care about the secret key. What he really cares about is the plaintext. So maybe it should be hard for the attacker to recover the entire plaintext. But even that doesn't work, because let's think about the following encryption scheme. So suppose what this encryption scheme does is it takes two messages. So I'm going to use two lines to denote the concatenation of two messages. M0 line M1 means concatenate M0 and M1. And imagine what the scheme does is really it outputs M0 in the clear and concatenates to that the encryption of M1, perhaps even using the one-time pad. Okay? And so here the attacker is going to be given one ciphertext, and his goal would be to recover the entire plaintext. But the poor attacker can't do that because here maybe we encrypted M1 using the one-time pad, so the attacker can't actually recover M1 because we know the one-time pad is secure given just one ciphertext. So this construction would satisfy the definition, but unfortunately, clearly this is not a secure encryption scheme because we just leaked half of the plaintext. M0 is completely available to the attacker. So even though he can't recover all of the plaintext, he might be able to recover most of the plaintext, and that's clearly insecure. So of course we already know the solution to this, and we talked about Shannon's definition of security, perfect secrecy, where Shannon's idea was that in fact when the attacker intercepts a ciphertext, he should learn absolutely no information about the plaintext. He shouldn't even learn one bit about the plaintext, or even he shouldn't even be able to predict a little bit about a bit of the plaintext. Absolutely no information about the plaintext. So let's recall very briefly Shannon's concept of perfect secrecy. Basically we said that, given a cipher, we said the cipher has perfect secrecy if given two messages of the same length. It so happens that the distribution of ciphertexts, if we pick a random key and we look at the distribution of ciphertext, we encrypt M0, we get exactly the same distribution as when we encrypt M1. The intuition here was that if the adversary observes the ciphertext, then he doesn't know whether it came from the distribution, the result of encrypting M0, or it came from the distribution as the result of encrypting M1. And as a result, he can't tell whether we encrypted M0 or M1. And that's true for all messages of the same length. And as a result, the poor attacker doesn't really know what message was encrypted. Of course, we already said that this definition is too strong in the sense that it requires really long keys. If a cipher that has short keys can't possibly satisfy this definition, and in particular stream ciphers can't satisfy this definition. Okay, so let's try to weaken the definition a little bit, and let's think to the previous segment, and we can say that instead of requiring that the two distributions be absolutely identical, what we can require is that the two distributions just be computationally indistinguishable. In other words, a poor, efficient attacker cannot distinguish the two distributions, even though the distributions might be very, very, very different. But just given a sample for one distribution and a sample from another distribution, the attacker can't tell which distribution he was given a sample from. It turns out this definition is actually almost right, but it's still a little too strong. This still cannot be satisfied. So we have to add one more constraint, and that is that instead of saying that this definition should hold for all M0, M1, it needs to hold for only pairs M0, M1 that the attacker can actually exhibit. Okay, so this actually leads us to the definition of semantic security. And so, again, this is semantic security for a one-time key. In other words, when the attacker is only given one ciphertext. And so the way we define semantic security is by defining two experiments. Okay, we'll define experiment 0 and experiment 1. And more generally, we'll think of these as experiment parenthesis B, where B can be 0 or 1. Okay, so the way the experiment is defined is as follows. We have an adversary that's trying to break the system, an adversary A. That's kind of the analog of a statistical test in the world of pseudo-random generators. And then the challenger does the following. So really we have two challengers, but the challengers are so similar that we can just describe them as a single challenger that in one case takes as input the bit set to 0, and the other case takes as input the bit set to 1. And let me show you what these challengers do. The first thing the challenger is going to do is it's going to pick a random key, and then the adversary basically is going to output two messages M0 and M1. Okay, so this is an explicit pair of messages that the attacker wants to be challenged on. And as usual, we're not trying to hide the length of the messages. We require that the messages be equal length. And then the challenger basically will output either the encryption of M0 or the encryption of M1. Okay, so in experiment 0, the challenger will output the encryption of M0. In experiment 1, the challenger will output the encryption of M1. Okay, so that's the difference between the two experiments. And then the adversary is trying to guess, basically, whether he was given the encryption of M0 or given the encryption of M1. Okay, so here's a little bit of notation. Let's define the event WB to be the event that in experiment B, the adversary output 1. Okay, so that's just an event. That basically in experiment 0, W0 means that the adversary output 1. In experiment 1, W1 means the adversary output 1. And now we can define the advantage of this adversary, basically to say what this is called the semantic security advantage of the adversary A against the scheme E, to be the difference of the probability of these two events. In other words, we're looking at whether the adversary behaves differently when he was given the encryption of M0 from when he was given the encryption of M1. And I want to make sure this is clear, so I'm going to say it one more time. So in experiment 0, he was given the encryption of M0. In experiment 1, he was given the encryption of M1. Now, we're just interested in whether the adversary output 1 or not in these experiments. If in both experiments the adversary output 1 with the same probability, that means that the adversary wasn't able to distinguish the two experiments. Experiment 0 basically looks to the adversary the same as experiment 1, because in both cases it output 1 with the same probability. However, if the adversary is able to output 1 in one experiment with significantly different probability than in the other experiment, then the adversary was actually able to distinguish the two experiments. Okay? So, to say this more formally, essentially the advantage, again, because it's a difference of two probabilities, the advantage is a number between 0 and 1. If the advantage is close to 0, that means that the adversary was not able to distinguish experiment 0 from experiment 1. However, if the advantage is close to 1, that means the adversary was very well able to distinguish experiment 0 from experiment 1, and that really means that he was able to distinguish an encryption of M0 from an encryption of M1. Okay, so that's our definition. Actually, that's just the definition of the advantage. And then the definition is just what you would expect. Basically, we'll say that a symmetric encryption scheme is semantically secure if for all efficient adversaries, here I'll put this in quotes again, for all efficient adversaries, the advantage is negligible. In other words, no efficient adversary can distinguish the encryption of M0 from the encryption of M1. And basically this is what it says repeatedly, that for these two messages that the adversary was able to exhibit, he wasn't able to distinguish these two distributions. Now, I want to show you, this is actually a very elegant definition. It might not seem so right away, but I want to show you some implications of this definition, and you'll see exactly why the definition is the way it is. Okay, so let's look at some examples. So the first example is, suppose we have a broken encryption scheme. In other words, suppose we have an adversary A that somehow, given the ciphertext, he's always able to deduce the least significant bit of the plaintext. Okay, so given the encryption of M0, this adversary is able to deduce the least significant bit of M0. So that's a terrible encryption scheme because it basically leaks the least significant bit of the plaintext just given the ciphertext. So I want to show you that the scheme is therefore is not semantically secure. So that kind of shows that if a system is semantically secure, then there is no attacker of this type. Okay, so let's see, why is the system not semantically secure? Well, so what we're going to do is we're going to basically use our adversary, who's able to learn the least significant bits. We're going to use him to break semantic security. So we're going to use him to distinguish experiment 0 from experiment 1. Okay, so here's what we're going to do. We're algorithm B. We're going to build algorithm B. And this algorithm B is going to use algorithm A in its belly. Okay, so the first thing that's going to happen is, of course, the challenger is going to choose a random key. The first thing that's going to happen is we need to output two messages. The messages that we're going to output basically are going to have different least significant bits. So one message is going to end with 0 and one message is going to end with 1. Now what is the challenger going to do? The challenger is going to give us the encryption of either M0 or M1, depending on whether we're in experiment 0 or in experiment 1. And then we just forward this ciphertext to the adversary. Okay, to adversary A. Now what's the property of adversary A? Given the ciphertext, adversary A can tell us what the least significant bits of the plaintext is. In other words, the adversary is going to output the least significant bit of M0 or M1. But lo and behold, that's basically the bit B. And then we're just going to output that as our guess. So let's call this thing B prime. Okay, so now this describes the semantic security adversary. And now you tell me, what is the semantic security advantage of this adversary? Well, so let's see. So in experiment 0, what's the probability that adversary B outputs 1? Well, in experiment 0, it's always given the encryption of M0, and therefore adversary A will always output the least significant bit of M0, which happens to be 0. In experiment 0, B always outputs 0, so the probability that it outputs 1 is 0. However, in experiment 1, we're given the encryption of M1, so how likely is adversary B to output 1 in experiment 1? Well, it always outputs 1, again, by the properties of algorithm A, and therefore the advantage basically is 1. So this is a huge advantage. It's as big as it's going to get, which means that this adversary completely broke the system. Okay, so we consider, so under semantic security, basically just deducing the least significant bit is enough to completely break the system under a semantic security definition. Okay, now the interesting thing here, of course, is that this is not just about the least significant bit. In fact, take any predicate of the message, for example, the most significant bit, bit number 7, maybe the XOR of all the bits in the message, and so on and so forth. Any kind of information, any bit about the plaintext that can be learned basically would mean that the system is not semantically secure. So basically all the adversary have to do would be to come up with two messages, M0 and M1, such that under one thing that A learns, it's the value 0, and under the other thing, the value is 1. So for example, if A was able to learn the XOR of all the bits of the message, then M0 and M1 would just have different XORs for all the bits of their messages, and then this adversary A would also be sufficient to break semantic security. Okay, so basically if a cipher is semantically secure, then no bit of information is revealed to an efficient adversary. Okay, so this is exactly the concept of perfect secrecy, only applied just to efficient adversaries rather than all adversaries. So the next thing I want to show you is that in fact the one-time pad in fact is semantically secure. It had better be semantically secure because it's more than that, it's perfectly secure. So let's see why that's true. Well, so again, it's one of these experiments. So suppose we have an adversary that claims to break semantic security of the one-time pad. The first thing the adversary is going to do is he's going to output two messages, M0 and M1, of the same length. Now, what does he get back as a challenge? As a challenge, he gets either the encryption of M0 or the encryption of M1 under the one-time pad. And he's trying to distinguish between those two possible ciphertexts that he gets, right? In experiment 0, he gets the encryption of M0, and experiment 1, he gets the encryption of M1. Well, so let me ask you, so what is the advantage of adversary A against the one-time pad? So remember, the property of the one-time pad is that K XOR M0 is distributed identically to K XOR M1. In other words, these distributions are absolutely identical distributions, identical. This is a property of XOR. If we XOR the random pad K with anything, either M0 or M1, we get uniform distribution. So in both cases, algorithm A is given as input exactly the same distribution, namely the uniform distribution on ciphertexts. And therefore, it's going to behave exactly the same in both cases because it was given the same distribution as input. And as a result, its advantage is 0, which means that the one-time pad is semantically secure. Now, the interesting thing here is not only is it semantically secure, it's semantically secure for all adversaries. We don't even have to restrict the adversaries to be efficient. No adversary, doesn't matter how smart you are, no adversary will be able to distinguish kx or m0 for kx or m1 because the two distributions are identical. Okay, so the one-time pad is semantically secure. Okay, so that completes our definition of semantic security. And the next thing we're going to do is prove that a secure PRG, in fact, implies that the stream cipher is semantically secure.